Hello, my name is Tony Botting and I'm a simulation specialist at GoEngineer. In this video we'll explain the shell offset definition. This is a T-junction structure with solid geometry that is fixed and the surface geometry that is 3 inches wide by 5 inches long. The solid geometry is meshed with solid elements. Now the surface geometry, which is also called a reference surface, is meshed with shell elements. I've given the shell elements a thickness of 1 inch and I've put an upward force on the end. This view shows how the structure would appear if we chose an all-solid approach. So, if you want to use the surface and shell approach, the surface geometry is normally located in the middle of this component, as you can see by the blue edge. This surface identically represents what is called the mid-surface of the part. In this image, I've identified the shell mid-surface as a red-colored dashed line. So, the blue-colored reference surface and the shell mid-surface are directly on top of each other. This is the default setting when you mesh a reference surface with shell elements. Note that it is not efficient to use shells for this particular part due to the low aspect ratio. Shells are typically warranted when the length to thickness ratio, or aspect ratio, is over about 20:1, as in this part. However, we'll use the shorter version just to demonstrate the shell offset function. After we run, the results of the stress field help identify the outline of the virtual structure thickness of 1 inch. You can see the stresses at the T-junction are pronounced up here and down here, relative to the reference surface. This indicates that the shell element mid-surface is positioned directly on the reference surface. To continue, we need to define reference directions and something called shell bottoms. For orientation, I'll call the plus z-axis my up direction, and I'll call the negative z-axis direction the down direction. Let's mesh this structure. When you mesh a structure with shells and visualize the mesh, you'll notice one side of the shells defaults to an orange color. The orange side is known as the shell bottoms. The word bottom does not refer to any particular direction. You can flip the shell bottoms to either side of the reference surface as I'm showing here. For this explanation, I'll flip the shell bottoms so the orange color faces downward. Keep this in mind as we continue. Okay, now we'll look at the shell offsets. If you edit the shell definition, there is an offset control panel where you can alter the position of the mid-surface relative to the reference surface. The offset value here is the percentage of the thickness value up here, from which the shell mid-surface distance is measured to the reference surface. It is a signed value and the default is 0. In each of the 4 icons, there is a cross-section or end view of the virtual structure as shown as a black rectangular outline. The reference surface that you select to define the shells is represented by the dark blue colored line. On this image, I've selected the second icon, and you can see the percentage value is changed to plus 0.5. This means if we measure up from the mid-surface to the reference surface, we'd get 50% of 1 inch or 1/2 inch. This composite image shows the results. You can see that the reference surface represents the upper virtual surface of the structure by examining the stress plot. The virtual mid-surface is shown as the dashed red line. So if we measure up from the dashed red line of the mid-surface to the reference surface, we get a value of plus 50% of the shell thickness. Okay, now we'll do this again, but this time select the third option. Notice the value is minus 0.5 and the blue line or reference surface is at the bottom of the virtual structure cross-section. This composite image shows the results. You can see the virtual mid-surface as the dashed red line. If we measure down from the dashed red line of the mid-surface to the reference surface, we get a value of minus 50% as shown by the offset value. Recall that all of this analysis is contingent on the shell bottoms facing downward. Here is what happens if we flip the shell element bottoms to face upward. This composite image shows plus 50% offset and shell bottoms facing upward. Notice now the reference surface is down below the virtual mid-surface according to our definition of up and down. This seems to contradict the value shown in the offset dialog. In summary, just remember to observe the shell bottoms. If you flip the shells so that the shell bottoms face downward as in this view, then the settings in the offset dialog will make sense according to this definition of up and down. In this video, we provided examples to explain the shell offset definition.